In this video, I'll talk about the relative reactivity of carboxylic acid derivatives. So here we're going to be primarily talking about acid halides, and the most common one is obviously the chlorine in here, but the X could have been chlorine, bromine, and iodine. And then I will be talking about the anhydride, that's the second one right there. We have an ester, we got the amide. So the amides could be primary, secondary, and tertiary, but they would have the same reactivity compared to the rest of the derivatives. So the second one here is the anhydride. This one is an ester, and that one is an amide at the end of the day here. And we got the acid halide here. And like I said, the most common one would be the acid chloride. So out of all of them, your acid halides are going to be the most reactive. So I'll say most reactive on the left side, and your least reactive is going to be the amide. And for that reason, you can make one derivative from another derivative, but it has to go in a certain way. So you can make a less reactive derivative from a more reactive derivative, but not the other way around. So what that means, I have a one-way path here for going all these to the right side. So I can go ahead and say I should be able to make, let's say, from acid halide, I should be able to make acid anhydride. I should also be able to make an ester. I'm not going to talk about how you're going to be making those. I'll kind of briefly talk about it, but not in too much details. But right now, you just need to know the general trend here. And you can also make amide from here, just like that. Now, when it comes to an anhydride, for example, this one, again, I can make any derivative that's onto the right side or less reactive to the anhydride. However, I cannot make the acid halide from the anhydride. So I can say from anhydride, I can go ahead and make an ester again. I can go ahead and make an amide from there. Okay, and from the esters, I cannot make anhydride and acid halide. However, I can go ahead and make an amide from there. So that's how you want to look at it. And how you make those, it's kind of very similar setup from one carboxylic acid derivative to another carboxylic acid derivative, as long as you can make them. And then all these derivatives that you have, they all have a capacity to go ahead and hydrolyze to its parent, you can say, which is the carboxylic acid. Now, let's suppose if I have an ester and I want to make it an acid chloride from there or an acid halide from there. So how would I really do that? Now, in order for me to make an acid halide from an ester, I cannot go directly backward. However, I can go ahead and hydrolyze the ester to an acid form, and from the acid, I can go ahead and make an acid halide. Most of the derivatives can be retrieved from the acid, so you have to be a little bit selective with your conditions, but you should be able to retrieve most of these derivatives from the acid itself, but it may not be the most efficient way sometimes. Sometimes you be better off kind of starting out with an acid halide here. So I can go ahead and say, if I have an amide, I can go ahead and hydrolyze the amide to an acid. I can go ahead and hydrolyze the ester to an acid. I can go ahead and hydrolyze the anhydride to an acid. I can also go ahead and hydrolyze the acid halide to an acid. And then to hydrolyze these things, you can either do the hydrolysis under acidic condition, or you can do that under basic condition. So either one of those are fine. So I can say either I'll do H3O plus and heat, or I will be doing that OH minus with water and heat. So it really depends on if I'm using the base, I will be making a carboxylate ion. That's really the difference that you got in there. So all of those would actually work fine here. So I can probably write them down for every one of those. So it kind of looks busy, but you can hydrolyze all of those back to the carboxylic acid derivative. Remember, if you were using it in a base, so when I was hydrolyzing this with an OH minus water and heat, the first thing you would make is the carboxylate ion. You are not going to be getting the acid directly, but the carboxylate ion. And then after that, in the second step, in the next step, you can go ahead and hydrolyze, or you can do an acid workup to get the acid. But either way, get something similar, and to go from an carboxylate to an acid is not going to be a problem. So and then the other thing you want to know, I can actually go ahead and from the acid, I can go ahead and get all these derivatives for the most part. So for example, if I want to go ahead and make an acid chloride from here, a typical reagent I use would be SOCl2, or I can use PCl3, or even I can use PCl5. So any one of those would work. And to make it an anhydride, so yeah, I'm just going to go ahead and put it right here, actually. To make it an anhydride, I can just use another of this acid, or even I can use ROCl there. I can use acid halide actually to make the anhydride, because that's going to be in a good leaving group. But you can certainly use another acid in the presence of a strong acid or something like H2SO4, so that works out fine as well. Um, and then if I want to make an ester, that's a very common one. You can go ahead and do an Fischer esterification to make ester directly from the acid. So I can use some sort of alcohol and an acid. I'll just heat it up. So that's an Fischer esterification, very common reaction that you can run. And then from the acid to the amide, that one is a little bit tricky, and you got to be really careful with how you run it. You can certainly go ahead and run this reaction. I can use like NH3, or even if I want to make a secondary amide, I can use, or if I want to make secondary amide, I can use primary amine, something like RNH2. But I have to have a coupling reagent with it. That's all I think. So a typical coupling reagents that's used is a DCC is one of the most common coupling reagents you're going to be seeing. That's not the only coupling reagent, but that is one of the most common coupling reagents you're going to be looking in here. So the whole job of the coupling reagent is making sure that you make this OH in a good leaving group, because in a lot of those cases the whole purpose will be to kind of go ahead and make this in a good leaving group for the most part. Like for example, if you're running this under acidic condition, you would be able to protonate it, and as a result, that would be in a good leaving group. In case of the NH3. The problem with the NH3 is that the NH3 is also in a base, so it has a potential to deprotonate that. So you first add the coupling reagent. So what coupling reagents do is they react with this oxygen and eventually makes this side as in a good leaving group before the amine steps in to do the nucleophilic attack on that carbon. So I'm not going to talk about the mechanism, but just understand the big picture, how you can go from one carboxylic acid derivative to another carboxylic acid derivative, and what their reactivity orders are. And like if I want to go back here, and like I said, I can go ahead and make an anhydride, for example, from the acid chloride. So when I'm making the anhydride from the acid chloride, I can certainly go ahead and use something like this, O, then an O minus. Because what it's going to do is going to do it in the backside attack here, and this is going to leave eventually, because the X is a good leaving group here, and you ended up getting this. Now when you want to make an ester, I can go ahead and use either an R prime OH, like an alcohol, um, within a base, something like pyridine, or even I can just use OR minus, just as that in a direct base as a nucleophile as well. So that would work fine. And if I want to make an amide, I would be using NH3 excess. Okay. And then if I want to look at an anhydride to make an ester, I will do something similar. I'll have ROH um, with pyridine, or I can just directly use OR minus there. So the OR minus would be like a new strong base. So we didn't have to use the pyridine because, pyridine was used as a base just to kind of make sure you deprotonate that oxygen at the end of the day. And then from the anhydride, I can make an enamide again. It's a very similar setup. I can go ahead and change the color here actually. I can go ahead and just use NH3 excess. And then from the esters, I can go ahead and make an amide. Again, just go ahead and use NH3 excess. Sometimes if you don't want to use an excess NH3 or an amine, it really depends on what type of amide you want to make. If you're making in a primary amide, you just use an ammonia. If you're making in a secondary amide, they want to use in a primary amines and so on. So if you don't want to use an excess NH3, a lot of time you would see pyridine being used just to kind of make sure to kill any of the acid that's being made in there. But if you're using an excess ammonia, the part of that ammonia would be used to just carry out the acid-base reactions.